A video presentation of the cylinder lab report for AERO 302, Team 3, presented by the following team members: William Yu, Christy Bagaygay, Paul Manzer, and Holden Kurfess.
The purpose of experimentation was to determine if flow separation could be delayed and pressure drag reduced by generating turbulence in the boundary layer to keep it energized and attached for as long as possible. The goal of this was to create a narrower wake behind the cylinder and thus reduce pressure drag. Flow separation could be delayed in two different ways. One, by increasing surface roughness, and two, increasing the Reynolds number. Our findings were as followed. Increasing surface roughness significantly delays boundary layer separation. Pressure drag is reduced in the wake of the turbulent boundary layer as a result, and that a potential flow equation, 1 minus 4 sine squared theta, can be matched with experimental data.
So this is the schematic of the test setup for the lab. As you can see, we have the wind tunnel in which wind is entering through the inlet and exiting via the outlet. The cylinder is attached horizontally inside the test section and extends from wall to wall. With the setup, we also have a smoke machine which blows smoke into the inlet in order to make flow over the cylinder visible. There's also a laser shining down on the cylinder from the top of the wind tunnel for flow vis. Just like the first lab, the pressure data is taken from the scanning valve and is sent to LabVIEW. As LabVIEW collects data for each individual test, it then sends it to MATLAB where we can interpret the data.
Startup positions for the experiment were determined. One controlled the positioning of the laser at the top of the test section to help with the smoke visual. One recorded the flow of the smoke within the test section around the cylinder with a camera. One controlled the fan's RPM through the use of the VFD and took measurements of the respective Reynolds number in LabVIEW while exporting that data to MATLAB. One used MATLAB to make sure data is collected for further analysis. Shown from the previous slide schematic are the locations and dimensions of the test components, which are the wind tunnel, cylinder, test strip, smoke machine, and laser. Data was gathered by the instrumentation of the pressure ports, scanner valve, LabVIEW, MATLAB, camera, and variable frequency drive, which is the VFD. Before the experiment, the diameter of the cylinder and locations of different pressure ports on the cylinder were identified. Measurement of the cylinder diameter was taken through the use of a caliper. The scanner valve sensor system translates the reading for the 24 pressure ports around the cylinder, and each port was positioned 15 degrees apart from one another. The data acquired from wind tunnel testing flowed in the following pathway. The fluid velocity within the wind tunnel is driven by the fan power, which is controlled by inputs by the VFD. Pressure readings from the 24 pressure ports around the cylinder are then sent to the scanner valve for translation. In our tunnel setup, this data is then exported from the scanner valve to LabVIEW, where it is then inputted into a MATLAB script that outputs the data in a more easily evaluated form. The first set of data is taken at the wind-off condition in order to calibrate the ports. A reading was taken of the ambient temperature at the start of the lab because room temperatures can affect the flow to fluid, experimental results, and or the laboratory equipment. The wind tunnel is set to 100 RPM to see how big the Reynolds number would be. Observation of the Reynolds number is important because there was a constraint of it not going past 30 due to the fact that the cylinder would be prone to vibrations from vortex shedding. Before data is recorded for the low Reynolds number, the person who is responsible for the camera positions the smoke machine at the inlet when the fan is running at 100 RPM, and the smoke machine stays there for all runs. After the position of the smoke machine is determined, the person responsible for the laser will locate the best position to use the laser. For comparison data analysis, each run will undergo speeds of two different Reynolds numbers, a low Reynolds number of 12 and a high Reynolds number of 25. At each of the respective Reynolds numbers, LabVIEW collects 200 data points from each port. It sends the data to MATLAB, and the process is done twice to assure that the second time is more stable. In the first run, there was the condition of no test strip being used. After the testing with a high Reynolds number is done, the flow visual is then recorded at a Reynolds number of 5. This procedure is then repeated on a second run with the condition of installing a test strip, which is a plastic-like sandpaper material and taped onto the cylinder with aluminum duct tape. Data is recorded for both low and high Reynolds numbers and a flow visual, following the same procedure and taking 2 sets of data for each speed. For shutdown, the fan was turned off since the blades were already cooled after cycling to a lowered RPM for the flow visual. At the end of the experiment, a reading is taken of the ambient temperature and both the smoke machine and laser were turned off. Of our pressure ports in the bottom left image shows where the laminar boundary layer begins to separate velocities. At the leading edge of the cylinder, a stagnation point is formed where the oncoming flow is brought to rest. The pressure here is equal to the stagnation pressure, and ideally, the pressure coefficient is equal to 1. However, at ports 12 and 13, the experimental pressure coefficient is above 1 at the stagnation point. At either side of stagnation point, the flow accelerates around the forward surface of the cylinder, producing a drop in the pressure, as seen in the ports from 6 to 18 that are 90 to 200. Immediately adjacent to the cylinder surface, a thin boundary layer is formed, and the boundary layer is a region which drops rapidly to 0 to satisfy the no-slip condition at the cylinder surface. The figure shows that there is a slight differentiation with the surface pressure coefficient distributions at 2 Reynolds numbers at a low of 12 and a high of 25, compared with the theoretical distribution of laminar flow at 1 minus 4 sine squared theta from ports 6 to 18. The big difference between the measured and the theoretical value at ports 1 and 24 are explained by the fact that the pressure differential inside the wake is unsteady, and the downstream flow after the maximum thickness doesn't follow the anticipated deceleration that would occur on the rearward face of the cylinder. The boundary layer remains laminar from the stagnation point at the front of the cylinder to the point to where it separates at the maximum thickness. The resulting flow pattern is associated with a high drag on the cylinder, and as the flow swims 90 degrees from the stagnation point, the boundary layer separates because it anticipates the deceleration of the flow that would otherwise occur on the rearward face of the cylinder. Downstream of the separation, the flow quickly becomes turbulent and a broad wake is formed. The wake as a whole is unstable and rolls up into vertices. Because of the separation, the pressure remains low and constant over the rearward face of the cylinder. In previous slides, the trends show that the resulting plots of pressure coefficients and the angle of pressure measurement around the cylinder were consistent with the shape of the graph for laminar flow given by the expression 1 minus 4 sine squared theta. The Reynolds number will dictate when and where the boundary layer will transition from laminar to turbulent. The use of a test strip, which is located near the leading edge of the model, forces the boundary layer to transition at a known position. At a higher Reynolds number, the boundary layer on the forward face of the cylinder undergoes transition and becomes turbulent, resulting with a much lower drag on the cylinder. The turbulent boundary layer that is generated by the test strip is less susceptible to the adverse pressure gradients as it remains attached to the cylinder surface past the 90 to 270 degrees of incidence. As a result, the wake is much narrower.
The potential flow equation comes from a mathematical derivation from putting a source and a sink close together so that we're considering a uniform flow in combination with a doublet. Mathematical derivation of this is provided in not the next slide, but the slide after, so we'll be looking at that more closely. The usefulness of it depends on the assumptions that we made while deriving the equation. So the potential flow equation assumes inviscid flow, so the equation can be applied in regions of experimental data where viscous forces are not as dominant. However, when you apply it to regions where viscous forces are dominant, the equation 1 minus 4 sine squared theta doesn't match experimental data that well. In the previous slide, we talked about how inviscid flow was an assumption made to derive the potential flow equation. Because of this assumption, the usefulness of the potential flow equation in predicting the coefficient of pressure depends on where we apply it on the cylinder. Applied in regions where viscous forces are low, the equation describes experimental data very well. Applied in viscous regions, the exact opposite applies, or the exact opposite occurs. If you look at the 6 figures, we have the port numbers on the x-axis and the coefficient of pressures on the y-axis. On each figure are 2 curves. One curve represents the experimental data, and the other curve is the theoretical potential flow equation, 1 minus 4 sine squared theta. It's clear on each of the 6 figures, each and every one, that between ports 6 and 18, there is very close similarity between the theoretical and experimental data. And we know from this that between ports 6 and 18, this is where the region is non-viscid, because we did say that the theoretical equation describes the experimental very well if it's applied in non-viscous regions. Looking at the bottom right-hand schematic, the ports that are between ports 6 and 18 are the right-hand side of the cylinder. So if you think about the cylinder in terms of a clock, it's all the ports that are between the 12 and the 6, just the right-hand side of the circle. The potential flow equation comes from simulating flow over a circular cylinder with superposition of a doublet and uniform flow. What is shown on this slide is the derivation of the potential flow equation from the stream function and velocity potential equations associated with this doublet and uniform flow combination. These 2 equations, the stream function and velocity potential, are shown in the top left corner of the slide. U infinity represents the speed or magnitude of the uniform flow, K represents the strength of the doublet, and R and theta represent the point of interest in the flow given in cylindrical coordinates. Derivation of the stream function with respect to R and theta gives the velocity field of the flow in components of R and theta. Looking at John D. Anderson's text, Fundamentals of Aerodynamics 5th edition, we see that the interior of the cylinder could be treated as a solid, since the stream equation running through the stagnation points given by little r is equal to big R and theta is equal to 0 pi are the same. So because we're simulating the cylinder as with a doublet and a uniform flow, it doesn't actually know that there's a physical object like a cylinder in the flow, but we can treat it as if the interior were solid. So given this, we're left with velocity equations Vr and V theta. If we plug little r is equal to big R into the equations, we get Vr is equal to 0 and that V theta is equal to negative 2u infinity sine theta. So we're only considering the velocity at the surface now, and we see that Vr is equal to 0 and V theta is equal to negative 2u infinity sine theta. This basically just tells us that the flow over the cylinder has no radial component, and that it's all tangential flow across the cylinder given by V theta. If we plug this V theta equation into Bernoulli's principle, we see that the coefficient of pressure across the surface of the cylinder is given by 1 minus 4 sine squared theta. So this is basically the potential flow equation, that Cp is equal to 1 minus 4 sine squared theta, where we're only considering the surface of the cylinder and not the interior.
The drag force was calculated by summing an average of the pressure-induced drag located at the midpoints between ports, and the coefficient of drag was determined by dividing the drag force by the dynamic pressure. The resultant coefficient of drag was plotted against the Reynolds number of the flow at 2 speeds, 12 meters per second and 24 meters per second, corresponding to low and high Reynolds numbers, respectively. A presentation of the resultant plots follows in the next 2 slides. Comparing the coefficient of drag to the Reynolds number of an airflow at 12 meters per second, we can immediately see the effect adding a trip strip to the cylinder surface has on drag. There were 2 trial runs conducted, with and without a trip strip applied, to verify precision of data collection. The clustering of related runs indicates fairly good precision in the data collection. Note that the results for very low flow of 4 meters per second, collected for flow visualization purposes, was also included. Immediately we can see that the application of a trip strip results in a lower coefficient of drag related to the results with no trip strip. This can be correlated to the impact turbulent flow has on the boundary layer as it moves over the surface of the cylinder. At relatively low speeds, the boundary layer remains attached to the surface longer, resulting in a smaller wake profile and reduced drag. With a higher flow speed, the opposite occurs. The addition of a trip strip results in both an increase in drag force and Reynolds number. In this case, the kinetic energy of the turbulent flow causes an increase in total momentum of the airflow over the surface. This increase in momentum causes the separation of the boundary layer to occur much earlier than flow without the trip strip, resulting in a much larger separation area and increased drag. As with the low-speed tests, multiple runs were conducted with and without the trip strips. Additionally, the frequency at which the scanning valve sampled the pressure at the ports was increased to determine if such a change had any impact on the collection of data, and 2 additional test runs were conducted at the higher frequency with the trip strip applied. Note, the first run with the trip strip applied resulted in the trip strip falling off during the course of the test. The data was included but could be considered anomalous. The clustering of data suggests good precision with the change in frequency having a very minimal impact on the results. Considering the cross-sectional profile of a sphere is similar to the cross-sectional profile of a cylinder, a comparison of the experimental data can be made to the drag of the sphere versus Reynolds number. Image courtesy of NASA at www.nasa.gov. Although the drag coefficient values are different, the impact of having a smooth surface versus a rough surface is remarkably similar. The data suggests, at a Reynolds number of approximately 90,000, the drag caused by a smooth surface is higher than the drag of a rough surface. A comparison to the chart seems to validate this result. Further, at a Reynolds number of approximately 180,000, both the smooth surface and rough surface have similar drag coefficients, with the rough surface being slightly higher. Again, a comparison to the chart adds validation to the experimental results, suggesting at this speed an intersection of the drag force of a smooth versus rough surface.
The straw number is a unitless number composed of 3 values: characteristic length, free stream velocity, and frequency, with the characteristic length being constant and the free stream velocity and frequency being changeable. It is possible to see how the trip strip and velocity affect the straw number. When velocity is kept constant, the only variable in the test is the presence of the trip strip. I did not notice any difference in the frequency at which the vortices were shed. However, this is likely due to human error. When velocity is changed, we were able to see a difference in the straw number and the frequency at which the vortices were shed. These observations prove that the equation works and is useful. If the test was repeated again, a higher FPS video would be taken so that it would be easier to calculate the frequency and distinguish the effect that surface roughness has on the straw number.
More roughness helps the flow stay more attached for longer. In laminar and turbulent boundary layers, the flow speed decreases as you approach the surface, with fluid particles right at the surface having 0 velocity. The difference between a laminar and turbulent boundary layer is that turbulent boundary layers contain eddies that mix high-speed flow at the top of the boundary layer with slow fluid particles at the bottom surface. As a result, the surface level fluid particles in the turbulent boundary layer are forced to move more energetically. As this flow moves along the surface, the adverse pressure gradient is taking energy and momentum out of it until the pressure gradient finally wins and the flow begins to travel upstream. When these fluid particles collide with those coming downstream, the flow has nowhere to go but up and away from the surface. So these are the mechanics of flow separation, collision of fluid particles going both ways until it's forced up and away from the surface. So in summary, for turbulent and boundary layers, separation occurs further downstream because the eddies are energized and they have more momentum as opposed to those for a laminar boundary layer. In the figure provided in the bottom right corner, this is from one of Dr. Marshall's AERO 306 lectures, and in the 80-degree representation, it's just saying that laminar flow usually, or laminar boundary layers usually separate 80 degrees, but turbulent boundary layer will separate as far as 115 degrees. Some of our plots were not perfectly symmetric, and we have a couple theories on why. One is that since it's experimental data, it's very clear that due to noise or due to systematic error, we just will not get a perfect data. We won't get like that perfect 1 minus 4 sine squared data for the potential flow equation. And 2 other theories are, one, due to the trip strip placement not being symmetrical. So the cylinder has a circular cross section, and if the strip placement is not symmetric, that means they're not 180 degrees apart. Why that is, it's because when we are applying the trip strips, we have to be careful not to cover the pressure ports. So in a way, the pressure ports did dictate where we could put the trip strips, and that was not always 180 degrees. So if they're not symmetric, that means the boundary layers are being tripped in different areas, and we're going to be seeing different pressure readings or different coefficient of pressures if they're not tripped in the same area, just because, lack of symmetry. And another reason why is that the cylinder placement may or may not be symmetrical. We have this theory that if the cylinder is not at the vertical midpoint of the test bed cross section, so like if it's not at the midpoint of the height of the test bed cross section, that we will see different results due to wall interference. Now, wall interference described by NASA is that, because aircraft or whatever aerodynamic features are not usually constrained to a wind tunnel in nature. So when you do that, there will be interactions between the wall that you have to account for, and you have to make corrections. So some wall interference corrections that people usually make for more elaborate wind tunnel tests are corrections to dynamic pressure, Mach number, angle of attack. These are all described as first order corrections, and these are necessary when you're just operating inside a wind tunnel. Obviously, that's beyond the scope of this class. We did not account for any wall interference, which may or may not have made our plots unsymmetrical. That's likely not the biggest reason why. The biggest reason why would probably be due to the trip strips not being perfectly symmetrical, but that is something that we have thought of. One of the main goals of this lab was to see how surface texture and Reynolds number, what effects those two factors had on boundary layer separation and where the flow separated on the cylinder. So we thought it was appropriate that we'd ask ourselves what happens if you use a sphere or a ball instead of a cylinder. And this following information was taken from NASA's website. They did the study on spheres that are smooth and are rough and compared it with cylinders that are smooth and rough. And we saw that roughness, it did not matter whether it was a ball or a cylinder. If it were rough, it would transition to a turbulent flow at a lower Reynolds number, as opposed to a smooth cylinder, which would do it at a higher Reynolds number. So it doesn't matter if it's a ball or a cylinder. Roughness is better for getting to that turbulent flow at a lower Reynolds number. And we saw that if you take a smooth sphere and a smooth cylinder, that the smooth sphere is more aerodynamic at Reynolds number greater than 10. So this says nothing about the roughness. It's just if we're taking a smooth sphere and a smooth cylinder, that the smooth sphere is more aerodynamic than the cylinder. No mention of rough cylinders here or rough spheres.
Errors in our experiment. For example, eddies can develop in the test section from the boundary layers of the blades. Therefore, the flow direction is sometimes unknown, and this makes it difficult to set the pressure ports parallel to the stream. In addition, there is also fluid turbulence. If the flow is highly turbulent and contains backflows, the output can be wrong or different. Flows that hit the pitot tube from the side or in a large amount of angles can induce lowered measured velocities. Human error. At one point during the runs with the test strip became detached from the cylinder and may have contributed to bad data. Systematic errors in instrumentation. Pressure and velocity measurements with the pitot tubes are influenced by a chain of errors. Most of the measurement setups are linked through sensors, transducers, and data acquisitions, and each part would influence the measurement since there are relays in time for collecting data, and those relays adds to a deviation.
In conclusion, our team wanted to see how Reynolds number and surface roughness affected boundary layer separation and the drag coefficient. So increasing surface roughness significantly delays boundary layer separation across the board. This results in a reduction of the coefficient of drag in the wake of the turbulent boundary layer at 12 meters per second, And this proves the potential flow equation 1 minus 4 sine squared theta matches our experimental data. However, the opposite occurs at 24 meters per second, in that we actually see a rise in the coefficient of drag.